So these notes are going to cover the first part of factoring polynomials. So far, we've only factored polynomials that were quadratic, so the highest exponent was 2. Here we have a couple of techniques for factoring unique expressions with cubes. So we have a sum of cubes formula and a difference of cubes formula. A lot like the difference of squares formula, but with cubes. Were you to multiply this out, you would end up with a cubed plus b cubed again. And same thing with this one. If you distributed here, everything would simplify to a cubed minus b cubed. So you can use those two facts to help you factor certain cubic expressions. For example, this first one here, we have 16x to the fourth plus 54xy cubed. As it is now, you can't use difference of cubes because of this one x term, and neither of these is a perfect cube. So this is why you always want to look to factor out a greatest common factor first. So the greatest common factor of 16x to the fourth and 54xy cubed is a 2x. And after you factor 2x out, you're left with 8x cubed plus 27y cubed. And now we can use that sum of cubes formula. So we have a cubed plus b cubed. That's what we have. So that means that our a is going to equal 8x cubed, and b is going to equal 27y cubed. So then a is 2x, because 2 cubed is 8, and x cubed is x cubed. Similarly, b is 3y. So now to factor this expression, we just have to substitute these into the sum of cubes formula. So remember, first we had a 2x that was just out front. Then it says a plus b, so 2x plus 3y. And then the next parentheses is a squared. So since a is 2x, then we square 2 to get 4, and x squared is x squared, minus a times b, so 2 times 3 is 6, and then x times y is xy, and b squared is 9y squared, since 3 squared is 9, and y squared is y squared. So now this polynomial is factored. Sometimes when you use these, the sum of cubes or difference of cubes, you end up with a second expression here that is factorable. In this case, we didn't. Number 2 here, it looks like you could use sum of cubes since we have y cubed and x cubed and they're being added. But unfortunately, 5 isn't a perfect cube number. There's no rational number that you can cube to get 5. So this isn't, I mean, technically you could use difference of, or sum of cubes, but it wouldn't really be helpful. So since this is not a factorable polynomial, we call it a prime polynomial. Just like a prime number is one that you can't factor. A prime polynomial you can't factor. So here we have a summary of some factoring techniques that we've already learned. And they're also kind of written in the order of when you see a polynomial, the first thing you want to do is factor out a GCF from all of them. So regardless of what it looks like, if you can factor GCF out, you make your numbers smaller, and you can make the terms a lot easier to deal with. And then you want to see if you can use any of these formulas, starting with difference of squares. Then you start looking towards these other examples, if you have 3 or 4 or more terms. So this factoring by grouping, we've actually done this already. When we factor quadratic expressions, and the ones where the leading coefficient doesn't equal 1, and we split up that middle term, we're using a technique called grouping. So on higher degree polynomials, it doesn't show up that often, but when it does, it can save you a lot of time. So this example here, number 3, as it is right now, these groups So the first three terms and then the next three terms. If I factored out the greatest common factor there, I wouldn't end up with the same thing. So I'm actually going to switch the 4x squared with the 10x squared. So I'm going to rewrite this as plus 10x squared minus 4x squared minus 28x minus 40. So when I see this, your first instinct is probably to combine like terms here, but actually as it's set up, this works a lot better. And you're just going to kind of see it happen. So when I factor an x squared out of the first group of terms, so just from my two groups are here and then here. So from the first three terms, I factor x squared out. So I get x squared times x squared plus 7x plus 10. And from the next three terms, I can factor out negative 4. And, wouldn't you know it, I'm left with x squared plus 7x plus 10. So just like when we factored quadratics, we see that these parts are the same. So that means I can continue factoring the expression. So x squared plus 7x plus 10 is one factor. And my other factor is what was left on the outside. X squared minus 4. But wait, we're not done because we can actually continue factoring. So x squared plus 7x plus 10 can factor into x plus 2 times x plus 5, since 2 times 5 would give us 10, and then 2 plus 5 gives us the 7x. And x squared minus 4 is a difference of squares, so we know that factors to x plus 2 times x minus 2. So now this is completely factored. If they asked us to solve the equation, then we could actually set each of the factors equal to 0 in order to solve, and we get 4 solutions since there are 4 factors. This second example here looks particularly fiendish, but we're going to use the same technique, that factoring by grouping. So as they are right now, these groups are good. So this first one, notice that all three of those terms have an a cubed that can be factored out. So when I factor a cubed out, I'm left with x squared minus 6x plus 9. And then I can factor out negative b cubed from the next one. So I get x squared plus, rather x squared minus 6x, since we factored out negative b cubed. X squared minus 6x and plus 9. And since we ended up with the same thing in both of these parentheses, so these are the same in both, that means we can continue factoring by grouping. So one factor is x squared minus 6x plus 9. And the other factor is a cubed minus b cubed. But wait, we're not done, because x squared minus 6x plus 9 is a perfect square trinomial, actually. So x squared minus 6x plus 9, we would have multiplies to 9 and adds to negative 6. So that is x minus 3 squared. And then a cubed minus b cubed is a difference of cubes. So the difference of cubes, that means it factors to, so a cubed minus b cubed, we would get a minus b times a squared plus ab plus b squared. And now this is completely factored. So this last example, we have an equation that we want to solve. So right away you should see this is a sum of cubes, because 64 is equal to 4 cubed. So a cubed is 64x cubed, which means that a is equal to 4x. And b cubed is 1, so that means b is 1. So using that sum of cubes formula, we can get that this factors into a plus b, so 4x plus 1 times, so 4x squared would be 16x squared, then plus 4x, since that's a times b. Scratch that, that's minus 4x. Since the sum of cubes is a squared minus ab. So 16x squared minus 4x, and then plus b squared, which is 1. Now, one of our factors we can already, so to solve this we set each factor equal to 0. So 4x plus 1 equals 0, means that x would equal negative 1/4. But if we set the other factor equal to 0, 16x squared plus 4x plus 1, we end up with a quadratic equation that we have to solve. So we could solve it by factoring, but we would need to find numbers that multiply to 16 and add to 4. So that's not going to work. So we're actually going to use the quadratic formula to solve this one. And we get, so x equals negative 4 plus or minus the square root of 4 squared minus 4 times 16 times 1, all divided by 2 times 16. So when we continue simplifying this, we would get, this is 16 minus 16 times 4 is 64. So this simplifies to negative 4 plus or minus square root of negative 48 over 32. And the square root of negative 48 can be broken down into, since 48 is 3 times the square root of 16. This is 4 plus or minus 4i, since we had a negative inside the square root, times the square root of 3, all over 32. And then we can simplify, since both of these are 4s, and 4 divided by 32 would be 1 over 8. So one of our solutions was negative 1/4. The other ones are 1 plus or minus I times the square root of 3 all over 8. So what we get is this unit certainly involves the return of I, since we're solving for, sometimes these equations have some complex solutions. All right, so stay tuned for part 2.